Good evening, everyone. So today also we will be seeing one of the most important, assignment questions, right? So today we will be doing a recap of what we have seen, in the last class, and then we will be moving on to the new questions. Okay. So these are the questions like we have seen these in the last class. So moving on to the first question, obtain the directional derivative for a scalar field, so phi, okay, and they have given an equation at the point 0, 1, -1 in the direction of I cap plus j cap plus k cap. So we will be seeing the solution for this. To find the directional derivative of the scalar field, we will be using the gradient operator. Okay, so this is the formula for the gradient operator they have given, right? Where I, j, and k cap are the unit vectors, right, along these directions, and they are these dou by dou x, dou by dou y are the partial derivative operators with respect to x, y, and z. So now we have the formula for the directional derivative of the scalar field, where there is the formula. Okay, what will dot denote here? It is the dot product. Okay, and now the scalar field is phi of x, y, z, where they have given an equation, and now we need to find the directional derivative at this particular point. Okay, so first we will calculate the gradient of the scalar field at this particular interval, and we have just substituted the values in this formula, right? So we have taken an interval 0, 1, -1 and just substitute in the equation. So now we will, when you simplify, you will get the value as -9, right? Yes. So the directional derivative of the scalar field phi would be equal to -9. This would be the final answer. Okay. Moving on to the next question. Calculate the work done by a force, this is the equation, in moving a particle along the path defined by the equations. These three are the equations and then given two time intervals. So now in order to calculate the work done by the force F vector, so first we need to use the line integral of the force along that path. Okay. So what is the formula for that? This is the formula for the line integral. Okay. So where what are A and B? They are the initial and final values, and T and R dash of T are the position vectors, right? So what is R dash of T? It is the velocity vector. Okay. So now we have these three equations that they have given to us in the question and two intervals 0 and 1. So we will write down the formula for the position vector and the velocity vector. Okay, so now we will substitute the vectors into this integral. Okay, so once you simplify, you will get the value as 1. Okay, so therefore the work done by the force F vector would be equal to 1. Okay, moving on to the next question. So using the divergence theorem, evaluate, okay, where they have given an equation over the surface of a sphere with center at the origin, okay, and they have given radius as 8 units. So the divergence theorem, which was also known as the Gauss theorem, so what will that state? It will state that the surface integral of the dot product of, vector field F vector over a closed surface is equal to the volume integral, okay, of F vector. So this divergence theorem, mathematically how you can write? So this is the formula, right? What is S vector here? It is a surface area vector, and okay, now we want to evaluate the surface integral. This is the formula, okay, over the surface, and they have given radius as 8 units, right? So now we can use the spherical coordinates in order to parameterize the surface of the sphere. So the surface area vector formula is this, okay, and this is for the unit normal vector, okay. So now what is theta here in the formula? It is the polar angle, okay, and what is phi? It is the azimuthal angle, okay. The surface integral formula would be this, okay. So now in order to evaluate the divergence of the vector, so we have this formula, okay. So now we will just substitute the values in the formula, okay, and now we will be using the spherical coordinates. So just substitute those values that is given in the question. You would be getting the answer as 64 pi by 3. Okay. So this is the surface integral of our sphere. Okay. Moving on to the next question. Explain with the help of diagrams what spherically and cylindrically symmetric charge distributions are. Okay. What is the electric field at a point inside a hollow metallic sphere of radius r having volume charge density rho? Okay. So now, what is a spherically symmetric charge distribution? Okay. So it is an electric charge where the charge density is same at any point of the sphere centered at the origin. Okay. A cylindrically symmetric charge distribution is a distribution of electric charge where charge density is same at any point on a cylinder. Okay. This is the difference between spherically charged and cylindrically symmetric charge distribution. So we will see these two types of diagrams for these two types. Okay, so you can see the diagram here. So now coming to the electric field at a point inside the hollow metallic surface of radius r, okay, which has a volume charge density, and always the electric field inside the hollow sphere would be equal to 0, right? And because of Gauss law, what does it state? Electric field at any point inside a hollow sphere is 0, right? So why is it? It is because the electric field due to infinitesimal charge element at any point inside the sphere will cancel out with the electric field due to its opposite element, right? And therefore, if there is an hollow sphere which has a uniform charge density, the electric field would be equal to 0. Okay. So moving on to the next question. Two particles carrying 4c and minus 2c charges are placed on a 1 meter long straight line. We need to determine the point on the line joining these particles where electric potential they have given it as 0. Okay. So now in order to find the point on the line joining two particles where electric potential is 0, we need to find the position where electric potential due to the two charges will cancel out. Okay. So let us consider the distance of the point from plus 4c charge to be x and minus 2c charge to be 1 minus x. Okay. So what would be the electric potential due to the plus 4c charge? This would be the equation, right? And for minus 2c charge, this would be the equation. So now when we have the negative sign in front of this kq2, okay, which indicates that the potential is negative. Okay, so what is now we will set v1 and v2 to be equal. When we set these two v1 v2 be equal, v1 equation would be equal to v2 equation. That is what we have written here. So now we'll just simplify the equation, okay, and we will solve for x. So when we are solving for x, we will get the value of x as 2 by 3. Okay, so therefore, what will be the electric potential when it is 0 at a distance of 2 by 3 meter, okay, plus 4c charge, right? 1 by 3 meter from minus 2c charge. Okay, moving on. So explain the phenomenon of polarization of a dielectric. Show that when a dielectric material is filled between the plates of a capacitor, the value of capacitance will increase by factor of k, the dielectric constant of the material. Okay, we'll see the solution for this. So polarization of the dielectric material will refer to the process of aligning the electric dipoles. Okay, where if there would be a presence of an electric field, right? When a dielectric material is placed in an electric field, the positive charges in the atoms are attracted towards the negative plate, while the negative charges are attracted towards the positive plate. Okay, so always positive charges will get attracted to negative plate and negative charges to the positive plate of the capacitor. So when this happens, this process happens, there would be a separation of charges. Okay, when there is a separation of charges, it is going to create something called as the electric dipoles. Okay, so now the direction of this electric dipoles in the material is aligned with the direction of an electric field. Okay, the alignment of dipole will create an electric field which would be opposite to the direction of the external field. Okay, So now this opposing, when there is opposite external electric fields, it will weaken the electric field within the dielectric so that the potential difference would be reduced. Okay. So however, the charge on the plates will remain the same, where it will increase the electric flux density within the dielectric. Okay. So now we will consider a parallel plate capacitor, okay, which has a plate of area A and separation distance D filled with the dielectric material, thickness T and dielectric constant K. Okay, so what would be the formula for the capacitance of a parallel plate capacitor? This is the formula. Okay, so where this symbol will represent the permittivity of the free space. Okay, so when there is a dielectric material that is filled between the plates of a capacitor, there is an electric flux density, and we have the formula for that, right? So yes, so in the absence of the dielectric material, the electric field would be given by this formula. Okay, what is V here? It is the potential difference. Okay, and then they have given the formula for the electric field within the dielectric. Okay, so then we will calculate the electric flux density. Okay, so this is the formula for the electric flux density. So now when we have free charges, okay, the electric field which is due to the free charges, then this is the formula. Okay, and what is the total electric field? This would be the formula E free plus E dash. Okay, so now we will just substitute the values, and we will just substitute the value in this electric flux density formula. Okay, and what is the electric charges on the plate of the capacitor? That is given by D total into A. This formula. Okay, so now at finally we will calculate the capacitance of the capacitor. Okay, so we are getting this value. So the capacitance of the capacitor would be, dielectric material would be K times greater than the capacitance of the same capacitor without the dielectric material. Okay, so this is the final solution that we have got. So next, this homework, guys, I hope you remember this problem I had given for homework in the last class. So we will see the solution for this. Okay, determine the value of equivalent capacitance between points A and B for the combination of capacitor shown in the figure below. Okay, so this was the diagram that was given to us. So what do you call this? The this diagram which represents the parallel. Okay, so what is the charge that we have? The charge, right? First we will consider this part. Okay, you can see here. So what is that? 1 by C plus 1 by 2C. So we are getting the answer 3 by 2C. So now suppose there is 1 by C, which is nothing but C dash, okay, which is 2C by 3. So when we consider in series, okay, that was in parallel. So now when we consider the same in series, then we would get C double dash is equal to C dash plus C. This is the formula. Okay, there is very important formula we need to remember. So what is the value? 2C by 3 plus C. Substitute the value for C dash plus C. So what is the value that we would be getting? That is 5C by 3. Okay, so therefore the total capacitance would be 5C by 3, right? Yes. Moving on to the next question. The energy of a capacitor is 4. Okay, so after it has been charged by a 1.5B battery. Okay, so now we need to calculate its energy when it is charged by a 6-volt battery. Okay, so we will see the solution for this. So the energy stored in the capacitor is given by this equation. Okay, this equation will represent the energy that is stored in the capacitor. What is U here? It is the energy stored in the capacitor, and C would be the capacitance, and what is V here? It is the voltage across the capacitor, right? So now let the capacitance of the capacitor be C. Okay, and voltage we will consider as V1 when it is charged by a 1.5-volt battery, right? So what would be the energy stored in the capacitor then? Just substitute the value here. Okay, you would be getting as 4.0 millijoules. So now solving for C, taking by looking into this equation, you will solve for C. Therefore, we will be getting this value 3.56, right? So now we will see the second case when the capacitor is charged by a 6.0 volt battery, right? So what would be the voltage across it, which is V2? Okay. So now we will be using the same formula, which is as we have used for U1. We would be considering the same formula, but we will be substituting these values. So therefore, we have got this final value. So what would be the final value? The energy stored in the capacitor when it was charged by 6 volt battery would be this one. Okay, so this is the final answer that we have got. Moving on to the next question. Obtain an expression to show that the change in the quantity of charge enclosed in an arbitrary volume is accompanied by the net flow of charge inwards and outwards across the surface of the enclosed volume. Okay, so we will see the answer for it. So what does Gauss law state? We have seen this, which states that the net electric flux across any closed surface is proportional to the charge enclosed within that surface. So how will you write this Gauss law? Mathematically, this is the formula. Okay, what is phi here? It is the electric flux. Okay, across the closed surface, where E would be the electric field. Okay, dA is the small area element at the surface, and Q dash would be the total charge that is enclosed within the surface, and this symbol represents the permittivity of the free space. So now just we will differentiate it on both the sides of the equation. Okay, so we will get it as dou E by dou T. What is that? Time rate of change of electric field. Okay, so now we will use the divergence theorem equation. So this is the equation of the divergence theorem. Okay, so where E is the divergence of the electric field, okay, at any point within the volume enclosed by the closed surface. And what is dV? It is a small volume element. Okay, therefore we have this equation. So now we will consider the arbitrary volume, okay, within a region of space where we will have the non-zero charge density. Okay, so the charge density at any point within the volume is given by the symbol where the volume is enclosed by the closed surface S. Okay, so therefore what is the total charge formula enclosed within the surface S? This is the formula. Okay, so now we will take the time derivative and both the sides we will get this equation. Okay, so now we will use the continuity equation. So what does it state? It will state that the net flow of charge into or out of any closed volume is equal to rate of change of charge within the volume. Okay, so we will rewrite the right hand side RHS of the equation. So we would be getting this new equation. Okay, so what is J here? It is the current density. Okay, and dA is nothing but small area element on the surface. So now we will just substitute this expression for dq, okay, enclosed into the previous equation. So we would get this new equation, right? So this equation will show that the change in quantity of charge enclosed in the arbitrary volume will be accompanied by the net flow of the charge inwards and outwards across the enclosed volume. Okay, so as we have seen, as it is given in the RHS of the equation. So now this flow of charge will be described by the current density J. Okay, so what it is related to? It is related to the divergence of electric field within the volume. So which is given by the left hand side of this equation, right? Next question. A horizontal straight wire carrying 12 ampere current from west to east is in the Earth's magnetic field B. Okay, at this place B is parallel to the surface of the Earth, points to the north, and its magnitude is 0.04 milli T. Okay, so determine the magnetic force on 1 meter length. Okay, we need to determine at 1 meter length of the wire, and what is the mass they have given? 50 grams. Okay, calculate the value of current in the wire so that its weight is balanced by the magnetic force. Okay. So now the magnetic force on a current carrying wire is given by this formula. This is the formula for the magnetic force on a current carrying wire. Okay, what is F here? It is a magnetic force. I is a current, and what is L here? Length of the field, length of the wire, and B is the magnetic field. Okay, so now the wire is carrying a current of 12 ampere in this field, like from west to east. Okay, and the magnetic field B is parallel to the surface of the earth, which points to the north and which has this magnitude. So now, since the wire is horizontal, the length of the wire should also be in the horizontal direction, right? Since the wire is horizontal, the length L also would be in the horizontal direction. So now we will use the right hand rule. Okay. So now we can determine the direction of the magnetic force on the wire. So now if we point the thumb of our right hand in the direction of the current, okay, and the fingers in the direction of magnetic field, okay, and the palm of our hand will be in point in the direction of magnetic force. Okay, so thumb, which is for the current, okay, and fingers in the direction of magnetic field, and palm of our hand will point in the direction of magnetic force. Okay, so now in this case we will have the force that will be pointing upwards, which is away from the surface of the earth. So now we will find for the magnetic force on 1 meter length. Okay, just use the formula and substitute. You would be getting as 0.48 Newton. So what would be the weight of 1 meter length of the wire? Again, use the formula W is equal to M into G. Substitute the values, you will be getting as 0.49. So now in order to balance the weight of the wire with the magnetic force, we will have the current in the wire, right? Such that the magnetic force would be equal and opposite to the weight. Okay. So what would be the current formula? I is equal to W divided by L into B. Just substitute. You will be getting it as 12.25 ampere. So therefore, how much current do you need? That is 12.25 ampere we will need in order to balance its weight with the magnetic force. Okay. Next question. Using Maxwell's equation in free space, derive the wave equation for the magnetic field vector. Okay. So these are the Maxwell's equation that we have got. Okay. So delta into E is equal to 0, which is Gauss law for electric field, into B is equal to 0, which is Gauss law for the magnetic fields. Delta into E is equal to minus dou P by dou T, which is Faraday's law. Delta into B, which is this equation, which is Ampere's law. Okay. So now taking the curl of equation 4. Okay. When you take the curl of equation 4, you would be getting this equation, right? So now we will use the vector identity. Okay. We will use the vector identity and the fact that delta into B is equal to 0, which is in the free space. Okay. So then we will have this formula. So now when we use the vector identity from the equation 3, we can substitute where we will get this formula. Okay. So this is nothing but the wave equation for the magnetic field vector B. Okay. In the free space. So now when we have the magnetic field vector, which will propagate as a wave. So what is the speed of it? The speed is given by this formula. Okay. Which is the speed of light in vacuum. Right? Yes. So today we have seen, many questions. So in the next class also, we will be seeing the most important questions